Hello everyone, I am Soumya from Armacha Institute of Technology and Sciences, Rajampet. Today I am here to give a presentation on our project. The title of our project is Simulation of the Performance of Brushless DC Motor with Integrated Power Converter using ANFIS controller. It was performed under the supervision of Mr. B. Murali Mohan, Assistant Professor of the Department of EEE. The outline of our project includes objective of the project, introduction, existing method, drawbacks of existing method, proposed method, schematic diagram, advantages, applications, software and hardware requirements, simulation results, and finally conclusion. Objective. The main objective of our project is to develop a compact integrated power converter topology for a brushless DC motor drive system. Introduction. Nowadays, BLDC motors are widely used in many applications due to the advantages of high efficiency, high power density, and wide range of speed regulation. Power converters play a key role in BLDCM drive systems by making the connections of power source and the BLDCM with matched voltage amplitudes and power flow. So the optimal design of power converter topologies and control algorithm is quite necessary for improving the overall performance of the BLDCM drive systems. Existing method. In the existing method, three-phase voltage source inverter with a common three-switch leg is implemented with a front-end BBD converter. Because of implementing the BBD converter at the front end will result in high cost, large converter size and less power density. Drawbacks: large converter size, high cost, less power density. Proposal method. In the proposal method, a compact integrated power converter topology is implemented. Here T7 acts as a BBD converter which is integrated with the common three-switch leg of the three-phase voltage source inverter. By integrating the BBD converter with TVSI, the converter size will be reduced, cost is reduced, and power density will be increased. Schematic diagram. This is the schematic diagram of a project. Here, battery is the power source. C1 and L acts as a filter, and T1 to T7 are the MOSFET transistors. Here G represents the MOSFET terminal, which is gate. So G1 to G7 are the gates. When T1, T6, T5 is in on state, then T3, T4, T2 is in off state. Supply is given from battery. Here C1 and L acts as a filters and avoids ripples, and switches generates the pulses and is given to the motor. From the motor, the actual speed is measured. From C2, bus voltage is measured. Gate driving signals are generated based on the switching operation. Advantages: reduced size, low cost, high power density. Applications: BLDC motors are used in electric vehicles and aerospace applications due to their compact design, less maintaining cost, high power density. Software and hardware requirements. Software configuration. Here the operating system user is Windows 10. Application software is Matlab. Hardware configuration. RAM 8 GB. Processor is 15. Simulation results. Question: modulation waveforms of integrated power converter. Output 1. At bus voltage 48 volts and rotor speed 1500 R per minute, the boost duty ratio remains around 0.75. Although the magnitudes of three-phase modulation differences increase with the rising of rotor speed, they still remain lower than boost duty ratio, which can ensure stable modulation process. Output 2 is similar to output 1 with a different rotor speed, which is 2500 R per minute. Similarly, at bus voltage 60 volts and rotor speed 1500 R per minute, the boost duty ratio is around 0.8, which remains higher than control references at 1500 R per minute. Similarly, output 4 at bus voltage 60 volts and rotor speed 2500 R per minute. Gate driving signals of the common three-switch leg. At bus voltage 48 volts, there are two switches turned on and one switch turned off at any instant. Similarly, at bus voltage 60 volts, which satisfy the basic modulation principle of three-switch leg. Three-phase currents and DC bus voltages at steady-state operation. At bus voltage 48 volts 1500 R per minute, the DC bus voltage can be regulated to maintain the reference value 48 volts, and the three-phase currents of the BLDC are controlled to be sinusoidal stably by the proposed integrated control strategies. Similarly, three-phase currents and DC bus voltages displayed at different bus voltages and rotor speeds. Speed tracking performance under various speed references. Under different DC bus voltages, the rotor speed can track the reference values rapidly under sudden speed changes. Both in the steady states and the speed transition instance, the DC bus voltage can be regulated to the references reliably. Speed tracking performance with load mutations under different DC bus voltages. When a 10 ohm load power register is suddenly added or removed from a three-phase diode bridge rectifier, the DC bus voltage can still be stably controlled to reference values. ID and IQ waveforms under different DC bus voltages. Based on the proposed modulation and the control strategy, the rotor speed can also be regulated to track the reference reliably, even under sudden load mutations. Conclusion. By this, I conclude that by using ANFIS controller for a brushless DC motor with an integrated power converter can result in improved performance such as smoother operation, higher efficiency, and better accuracy. By integrating the power converter with DVSI results in reduced cost and overall system complexity. However, the actual performance of the system depends on the various factors such as motor specifications and controller used, the operating conditions and the application requirements. So further research and testing will be necessary to validate the effectiveness of this approach in practical applications. Thank you.